Hi there. Well, what I'd like to do now for you is show you how to find the x-intercepts of a certain trigonometry graph within the domain specified. Okay, and this is something which a lot of students don't seem to be able to get. So this is my 2 penneth worth on it, if that's helpful. Okay, so the question I'm going to address is finding the x-intercepts of 2 sine 2 times x minus pi on 3 minus root 3, what a mouthful, where x is going from 0 to 2 pi. Okay, now, the first thing that I like to do is I like to find what's called the working domain. Now, some people don't do that. They just basically just keep on churning out solutions until they know they're out of range. Well, I don't like that. I like to do something a little bit more precise. So let's have a little bit of a look at that and see how to do that. So we know that x goes from 0 to 2 pi, but that's not going to help us with our working domain. The working domain is the domain of what's behind the sine symbol. So, yeah, that's it. What domain would we have for that expression behind the sine symbol? That's what I want to address, okay? So let's do that. So, x goes from 0 to 2 pi, and I'm going to build up to that expression behind the sine symbol. So therefore, I can say that x minus pi on 3, you take pi on 3 off both of those limits of the x 0 to 2 pi domain, and what do you get? Minus pi on 3 to 5 pi on 3. Now all I've got to do now is double that, and I've got my working domain. How marvellous. Now, armed with that, I can find all the solutions when I set that equation equal to 0, that is y equals 0, which fit within that working domain. And once I do that, I just solve it for x, and it's as easy as. Okay, here we go. Solving for the x-intercepts, yep. So we've got y is 2 sine 2x minus pi on 3 minus root 3, and the x-intercepts are where y equals 0. Let's go. Okay, we get that. That's the original expression. And then we're going to say, okay, therefore that must mean if you set y equal to 0, that sine of 2 open bracket x minus pi on 3 close bracket equals root 3 on 2 when y equals 0. Okay, now that's a key point. And you say to yourself, root 3 on 2 looks mighty familiar. What angle is that? Well, let's get out our cast diagram, and we know that the basic angle in quadrant 1, which has a sine of root 3 on 2, is, yes, wouldn't you know it, pi on 3. Now, you knew that, didn't you? Because if you didn't, please learn them. Now, let's do the next bit. Yes, we need quadrant 1 and quadrant 2 because they are the quadrants in which the sine is positive, which is what we want in this instance. So let's go for that. We need all angles in the working domain which fit. So let's explore that now. We've got our basic angle, our little basic tool, our little spanner, and let's go for it. We do it in 2 stages because we've ended up with a working domain going from minus 2 pi on 3 right up to and including 10 pi on 3. We'll do the negative angles from 0 sort of backwards, if you like, and then we'll do the positive angles forwards from 0. That's right, that's what we're doing. Okay, that's what we've got to do. So let's pursue the backwards ones first, or in the negative direction. See how I'm going to signify that. See, that's the negative direction going clockwise is negative. Okay? Now, and I think you'll find, just looking at that domain from 0 backwards to minus 2 pi on 3, there ain't none. There ain't none. So it looks like we've drawn a blank in the first 2 quadrants. There's nothing there. So yeah, that minus 4 pi on 3 is the first one, and that's not within our working domain, is it? So we've got to cross it out. It's out of range. Oh, well, so much for that. Let's go for the positive ones and see if we have more success. Okay, now we're going from 0 to 10 pi on 3. So what do we get? Think about that. Going in the anti-clockwise direction, yes, the first quadrant yields pi on 3. The second quadrant yields 2 pi on 3. Now, all you've got to do now is keep leapfrogging by 2 pi to get all the corresponding second and third and subsequent revolutions, if you like, around that unit circle. So the next one, yeah, is pi on 3 plus 2 pi, which gets you 7 pi on 3. And the next one is you leapfrog the second term, add 2 pi, which is 6 pi on 3, which gets you 8 pi on 3. Isn't this fun? And then we get the next one, you leapfrog again, having a game of leapfrog. And I got 13 pi on 3. Uh-oh, 13 pi on 3. I think there's something wrong there. I think we're out of range. Oh, yes, we are. Oh dear, there goes the 13 pi on 3. But see how good that is when you do it with the working domain. You kind of know exactly what you're doing. And you don't have to sort of do the pot shot technique, which you have to do if you're just kind of generating solutions like firing bullets, you know, until you finally get one that's kind of out of range. So, okay, what was I saying? Oh yeah, so I summarise all that, all the negative ones, which in this case there aren't any, and all the positive ones, from the lowest, most negative, to the highest, most positive, and then you just solve it. That's the final step for x. Here it comes. So, we just work towards it. In that line there, I've just divided through everything by 2, and in the next line I'm going to add pi on 3, which I think I'll probably call it 2 pi on 6, because all those terms on the right hand side are over 6, which that'll make it easier for me to think. So I'll just rewrite that out. Seeing I've got a bit of a cold, I can't think. And let's go for it now. This looks very, very interesting. Now, gee, those terms look great, but I can do some final cancelling down now. That's my final step. Okay, I'm going to simplify that, and then I think I'm there. There it comes. There it comes. Now, if you're asked for coordinate points, intercept points, a point means coordinate points. So don't jolly well leave it like that if that's what you asked for, because that wouldn't be the answer. This would be the answer. You have to be so careful. Yeah, there it is. Ain't it grand? Ain't maths marvellous? So I think that's the end now. Yes, it's the end. And what is our little smiley face going to say now to us? Of course, it's fun. Okay. Thank you so much, everybody, and have a great day. See you next time.